You know that soda can you just tossed into the recycling bin? Well, MIT engineers have been testing ways to turn that into something we can use for fuel with hydrogen. Oh, this isn't some distant science fiction idea. A recent study from MIT shows that this can be low cost, reliable, and scalable using recycled aluminum and hydrogen from seawater to create a fuel. It sounds almost too simple to work, right? But there's some chemistry and engineering that we still have to work out. So let me talk to you about it. Hydrogen is often called the fuel of the future because when you burn it, there are no carbon emissions, just water vapor. And what's interesting is that over 95% of hydrogen today is made from fossil fuels, so mostly natural gas. And that process releases about 11 kilograms of CO2 for every kilogram of hydrogen produced. So ironically, most hydrogen production today isn't even clean. The greener alternative, splitting water with renewable electricity, is much cleaner, but it's still expensive, energy intensive, and kind of hard to scale. So this is where the MIT engineers' idea comes in. Use recycled aluminum cans and seawater, along with a clever chemical trick to make hydrogen on demand. Okay, so aluminum can split water into hydrogen and aluminum oxide, but in practice it doesn't because it forms a thin oxide layer that blocks the reaction. The MIT researchers overcame this by coating recycled aluminum pellets with a tiny amount of liquid metal alloy, gallium and indium, which strip off that oxide layer. So once treated, the aluminum reacts immediately with seawater, producing hydrogen gas and a mineral byproduct called Boehmite. But what's cool is the salt in the seawater causes most of the gallium-indium alloy to precipitate out, so it can be recovered and then used in the next batch. That dramatically reduces the need for these expensive and rare minerals. And aluminum is surprisingly energy-dense as fuel, meaning small amounts can produce a lot of hydrogen. So what does this look like at scale? Here's kind of the idea they're thinking. So instead of transporting compressed hydrogen, which is dangerous and expensive, you ship pre-treated aluminum pellets to coastal fuel stations. And then at the station, you mix the pellets with seawater to generate hydrogen on demand. That hydrogen could go directly into fuel cell vehicles or turbines. And the bonus is that reaction creates the Boehmite, a mineral used in semiconductors and coatings, which could then be sold to help offset costs. The researchers have even built a small prototype. It's about the size of a water bottle. And it can power an e-bike for hours. I know I would love to take that around town. They're now exploring underwater and off-grid applications where seawater is readily available. So now let's talk some numbers. In MIT's life cycle analysis, the process generates about 1.45 kilograms of CO2 per kilogram of hydrogen. So that's dramatically lower than fossil-based hydrogen. And it's in about the same ballpark as some green hydrogen technologies that are already powered by wind or solar. Cost-wise, they estimate it to be about $9 per kilogram of hydrogen, which is competitive with kind of the early stage green hydrogen that we're working on now in 2025. 1 kilogram of hydrogen can power a fuel cell car for roughly 60 to 100 kilometers, depending on the vehicle. Trade-offs. You need access to seawater, so the system works better near coastlines. And while gallium and indium are recoverable, they're still relatively rare and must be sourced sustainably. Plus, scaling up will require solving some big engineering challenges, like reactor durability, full material recovery, and the energy required to generate aluminum from its oxidized form. But comparing it to the infrastructure needed for large-scale electrolysis, it's surprisingly simple and potentially a lot cheaper. So what I'm taking away is that MIT's process, we can turn something as ordinary as a soda can and seawater into something incredibly valuable in the energy realm.